Hi there, my name is Thomas. I'm from investmentexcel.com, a platform for students and businesses that would like to retrieve material or perhaps supporting material within topics in finance and economics. The idea is that many issues, complex issues in economics and finance, they are at the end of the day best understood or intuitively understood by using a bottom-up framework developed in Excel. At least this is my experience and many of my friends' experiences, and this is what I have heard in all those many years I have worked as assistant professor at the universities, that once we apply some of the theoretical settings in Excel and try to manipulate the numbers and the formulas, many things make sense. And in this case, today, with path-dependent options, I consider that this is also the case here, because digging into the textbook on path-dependent options and Monte Carlo simulation, you will see a large range of complicated models and formulas and equations. So here I would like to demystify the path-dependent options by applying the Monte Carlo technique and by simulating many simple path-dependent structures from which we can derive a statistical distribution that is otherwise, with path-dependent options, often unknown. Obviously, this topic is slightly or perhaps even advanced, so feel free to go to the investmentexcel.com site and visit some of the other sessions we have made on simple structures, simple features in options, and also how to apply the Monte Carlo technique on more simple cases. This video and the Excel workbook are both available on investmentexcel.com and spotify.com. Alright, let's just take a look at what we call an Asian option. An Asian option is one of those complex options where we cannot readily rely on any analytical solutions. We need to use simulated prices or values to build our own statistical distributions from which we can price the option. We look at here is a European call option, and European, of course, by which we mean that there's only cash flow on maturity. By call, we always mean that it gives the holder of the option the long position and upside on the underlying development of the stock, in this case on the path-dependent price of the stock. So this constitutes an Asian style option, and normally we calculate the path dependency in the Asian options by either taking the simple arithmetic average of a path of stock prices, and in this case, with the structure here that I have 5 years, and we take the average of the stock price of all those 5 years, including the maturity date simulated price. So eventually the call option is the maximum of 0 and the average price minus the exercise price, which is 100. In order to simulate the stock price at all dates 1, 2, 3, 4, 5, remember I cannot only simulate on maturity date as we normally can with a European option without path dependency. We can just simulate on the last date. Here we simulate on all dates, and we simulate a stock, an underlying stock, in a geometric Brownian motion with a volatility of 20% of the stock return per year, and with a drift of 5%. And the drift of 5% is actually because we know that the path-dependent call option, or at least we assume that the path-dependent call option can be replicated in another portfolio. The profile of the option can be replicated in another portfolio, which can be shown to give only the risk-free return. So this is the classical no arbitrage argument from Black and Scholes that can be used here as well. So this essentially leaves us with a process that we call a risk-neutral process. And this means that we can discount the price that we get, or the value we get at the option at time maturity 5, we can discount that with the risk-free rate. So this price is de facto under the measurement Q. So it's priced by a dynamics with the risk-free rate, and it's discounted by the risk-free rate. And the reason why we can use the risk-free rate in the discounting, as I said, is because we have the replicating portfolio. So we know by construction or definition that the discounting must be the risk-free rate, and for simplicity we just assume that it's flat all the way out to 5. So a fancy financial derivative trader in Bank of America, he can build a portfolio that has the same profile as the path dependent option. He can build that with some other products, and the combination of those products will give 5%. So in order to avoid arbitrage between the two products, the straight up call option or the outright call option here and the replicating portfolio, then we need to have that the call option has a discount rate of 5%. And for this to be true, we need to have the expected, or we need to have the process, the stochastic process, to have a drift of 5% as well. And this changes the probabilities in the distribution, because it's another drift. It is a lower drift than if we had, say, 8% with a premium. So we shift the normal distribution at maturity, or at least the distribution. We don't know if it's normal. We shift it leftwards, and this makes the price or the value, average value on maturity lower, but we also discount with a lower price. So this is why we can use the risk neutral principle. Okay, the time is running. I will just go quickly into the simulated path, and as I said, we need to simulate on all dates because we need to take out a value on each date that we have to use in the process. So for instance, this one, average of this one. And here I have just first in this expression I have calculated a simulated log return exactly as I do in the Black and Scholes, and then I have exponentialized it. So this range, this simulated path here, is a log normal distribution of stock return. So no negative values are possible. And the same goes for the rest. Now what I just need is to, for all these draws, all these simulated path, I need for each draw to make an average as if this was the outcome. And if I do that for all simulations, I can ultimately calculate the average of the option price. So here's the corresponding option price, this price minus X, and see if that is lower than 0. So the lower bound here, there's one lower bound there in the call option structure. So now I just take the average of the call option, so of column 9, N. So this is the expected value of the call option at maturity, from which I need to take the value today. I need to discount the value today, and as I said, each period must be discounted by 5%, because that's the value of, that's the known return. It's not expected, it's known return of the replicating portfolio. So to avoid arbitrage in the structure, we need the call option price to be 14.73. And the same we could have done with a put or any other. We could have changed the average to 3 days or 2 days and so on. The idea here is that it's quite easy to calculate these more complex products as long as you use a simulation. And of course you can always calculate the Greeks, all the sensitivity parameters, by just changing, say for instance you like to calculate delta, you would change this by $1 up and down, and you will see the reflection in the price. So you would be able to see how sensitive the call option is to a change in an outright change in the underlying stock. And with time, theta, risk-free rate, raw, and so on. And over here, just lastly, you see the simulated payoff profile at maturity. And remember always, it's called an intrinsic value at maturity. There are no parameters in the formula at this point. And we see it here, how the asymmetric behavior is, the hockey stick as we call it. So yeah, the price of the option is almost $15, but then on the other hand you get an upside that the average stock price will drift upwards this, and you have no further downside. Alright, thank you.